again, I'm Dave Barr, Associate Dean for Faculty in College of Engineering, and it's my honor to introduce our panel moderator, Professor Leah Stanchu, who is the current interim head of Materials Engineering. So with that, Leah.
Thank you, Professor Barr. I am happy to introduce our panelists today, Professor Alejandro Strahan, who's a professor of materials engineering, and Arun Manodi. The last name is very hard. Yeah, so we will have a panel discussion, and I'm going to start with one question, and then I'm going to encourage you to participate in the discussion. So based on the talk that you have, it became evident that this material-driven paradigm in material science, data-driven paradigm is more and more present. How do you all think that the training and education of students, engineers, scientists need to change to keep up with this new paradigm? Whoever, yeah?
I've talked a lot.
Okay. Okay, well, let me first say what an honor it is to be here with, Dr. Perrson and Dr. Strachan. Okay, so the question is, if I understand correctly, about, we're talking about the fourth paradigm, talking about data, informatics, etc. How should training and education, etc., change to reflect that, right? So it is changing a bit because I asked a bunch of students in my class to attend it, and I can see some faces here. So first of all, it's working to some extent, right? Or some of them have left now, but it is working to some extent, right?
There was food.
Yes, there's food earlier, but even for the seminar, it was packed, right? So it's wonderful to see. So I think it's definitely changed. I started my PhD in 2012, and my PhD advisor told me, hey, Arun, have you heard of machine learning? Maybe we should start looking into that. Have you heard of data science, right? So it was very much in the, in the beginning, right? Not to say that people weren't doing it. Of course, so many people are already doing it, right? Computer scientists have been using it for decades, right? Neural networks have been around forever. But for materials engineers, especially undergraduate students who start using it, of course, there was kind of a backlog there, right? So more and more, of course, students are using it. When we get applications for students, there's already, students coming in who have already trained models, already worked with, a bunch of data science-based approaches. So the way we are addressing it is, of course, we are trying to integrate it as much into the curriculum as possible, right? Obviously, since my research involves these kinds of methods, any course I teach involves doing some kind of coding, maybe some kind of data analysis, data visualization, some kind of feature selection, dimensionality reduction, those types of things, right? So the way I have addressed it so far is first of all, out of the 575,000 registered users on Materials Project, I'd like to know how many I contributed to, because I certainly made people register, right? I asked students, have you used the Materials Project? The answer used to be different 5 years ago. Now, more and more students say yes to that question. 5 years ago, maybe they would say, not really. What is it about? What do you do with that? So, I think more and more students, experimental researchers are using it. While they're working in the lab, they probably are utilizing, the Materials Project and similar resources to get some information before they actually get started on their experiments or, on their work. So, I think, so we are kind of, starting to teach Python for materials engineers. That's kind of a new course that we just started. So we are hoping that everybody is now on the same page. All the undergraduate students have a basic understanding of how to write basic code, how to, use these databases, how to do data visualization, how to make, great plots that comes with, getting better skills or, in terms of these data visualizations and stuff. So I think, we are incorporating a lot of these things into our curricula. There are a lot of tools out there, so the barrier is much lower. If you want to run a DFT calculation, you can go to NanoHub, you can click on the DFT tool, just pick a bunch of parameters and just run it, right? That was not always possible, right? It's now pretty routine, even if you don't understand these things, right? So I think there's a lot of resources out there. I think a lot of us have already incorporated these things in our undergraduate and graduate courses. and a lot of other people who haven't yet, like, we kind of need to push people to, have, the data and the data science aspect of it and the materials data informatics aspect of it kind of incorporated in their courses and stuff, right? Okay, I'll talk more later. Maybe somebody else can take over. That was probably longer than it should have been.
I'd like to add two things, and I agree with Arun. First of all, one is understanding in terms of education that students should treat data with a little bit more carefully and using state-of-the-art techniques. I like what Kristin was saying about her students. First of all, you need to determine the workflows for your simulations. Before you do any science, make sure you're doing things right. Your results are reproducible, they're automatic or automatable, and then you go and have fun. And I think that needs to be adopted by the entire community. Whether you're a simulation person or you're an experimentalist, that has to be how we all work. And we all need to understand that every piece of data that we generate, once we create these workflows, whether experimental or theoretical, that are validated and verified and working, every single piece of that data that you generate needs to be shared in a repository like the materials project or whatever repository your field works. One of the big challenges that we have is that sharing the product of our work through publications is a very inefficient way of moving in the direction of data-driven science. So that's one aspect. We all need to treat data better. Every student as an undergrad needs to understand that the default should be that the data that you generate is automatically streamed and you have no choice into making it what we call fair, findable, accessible, interoperable, and reusable, which is not the same thing as open, but the data needs to be in a way that's machine actionable. And the other aspect of the answer is that we are just beginning to grasp what these AI tools can do and how they will affect education, okay? A lot of tasks that we're currently teaching may be completely irrelevant in a couple of years, including, by the way, teaching Python, probably, okay? And so the question, I think, for the students sitting here is going to be, what are the fundamentals that you're learning? What Kristin was saying about OpenAI, they probably, they need us because of our role in workforce development. They need academia, but they also need domain experts, right? And that is going to be, that is what you're, as engineering students, as physics, chemistry students, that's what you need to develop and what we need to teach you. And I think a lot of the other skills are not going to be that important. I think, I'm old enough that, Kristin was saying, and I'm not saying you're old.
I'm old. It's okay.
That when she got a PhD or I got a PhD, just being able to run these simulations, you could get a job just because you were able to run DFT, right? That was the skill that you needed. Yeah. Very few people could do it. Now, you just talk to the computer and the computer runs the DFT for you, right? And so that skill, being able to run the code, know about HPC, that's going to be irrelevant. And it is becoming very quickly irrelevant. So we need to think at a higher level when we think about educating students.
Yeah, Jarvis is almost a reality.
Yeah.
I guess.
Yeah, I completely agree. I do. I think we have a tendency to react of like, oh, which class am I now going to take out of the undergraduate curriculum to replace it with a machine learning class? Because that's obviously what the students need to know. But I've found, experience-wise, that I can take, if I take any good trained material scientist with a little bit of interest in programming, I mean, not hating programming, let's put it that way, I can turn that person into a truly data-savvy machine learning expert in a very short amount of time. I cannot do the reverse. I cannot take a CS expert who is really good at machine learning and turn them into a material science expert in a short amount. And I've tried. I really have. Like, I've had people embedded in my team that came from that direction. It was really difficult, and it took years and years of this sort of translational sort of talking, working together. I'm not saying interdisciplinary is like we should be doing that, and these people who know both are bridges, but it's much harder to go from one direction to the other. It's very sort of hysteresis-like. So yeah, be very happy and proud about your domain knowledge, because that is irreplaceable.
I completely agree with that, by the way. In my experience too, much easier to teach an actual material student the data, ML relevant skills than the other way around. So that domain expertise is essential. Yeah.
I have a little story. Can I add a little story? Okay, so machine learning story on domain knowledge. If you've seen MapMiner, right, you can take any data set and shove it into MapMiner, featureize it, and get something out of it. That's sort of very doable. So I had a data set on NMR chemical shifts for various amounts of oxides. And I had one student who had never done NMR. He was a material scientist, but had never done NMR. And he took MapMiner and he shoved the NMR data set in there, and he kind of just got a scatter of cloud points everywhere. He couldn't make it work. So we kind of go, oh, NMR is really tricky, probably can't be machine learned, whatever. So I rested for a while. Then along comes a student from Ohio State who had worked his entire undergraduate on NMR. He takes the same data set, looks at the MapMiner features and goes, no. So he designed his own feature, which was basically like these little Zeppelin balloons, like two axes and whatever, to sort of expand the spectra into those kinds of axes. And suddenly all the points lined up beautifully. And he with the same data set. So understanding your data set from the domain perspective, whether it's characterization or properties, is really important in machine learning. If you just throw the black box of MapMiner at it, you have to be a bit lucky. Or maybe you have a really large data set and deep learning works, right? But it's very rare that we have that. So yeah, understanding your data set.
Thank you. I could ask other questions, but I would like to give the opportunity from the audience.
I'd like to ask an easy question to come up with, but perhaps harder to answer. I liked at the beginning of your talk that you had the 4 paradigms from inspired by your colleague. What's the 5th? And I'm wondering, is it fully autonomous research? I would argue that's still part of the 4th because it's data-driven. So what is that 5th? And maybe to help answer that, did you imagine this 4th was coming before it got here?
Well, first of all, what is the 5th? So I think there are some people out there already that are saying that we're climbing, we're touching the 5th. I'm not sure I agree with them that the 5th is that different than the 4th. I think we can have all kinds of discussions around that. But there are people suggesting that as these machine learning models, which we're already seeing in companies, are now generating the new training data, it becomes almost self-propelling, and that could be if that truly generates new knowledge or new vehicles, maybe that is the 5th. But currently, I'm seeing it as part of the 4th too. So I'm not sure. Did I see the 4th paradigm? Not as such, but I think, like Ala was saying, that in terms of the value of data, I think that I've always respected. That, value your data, because the data and more data, I saw my students when they got more hands, and when I saw the Duracell data and I dug into it myself, there is a world that opens up when you suddenly have access to more data and better data. And that I think is important. It's actually at the core of material science when you think about it. We are inherently a very data focused community, because we didn't have a lot of easy equations that did everything for us. We had to what does the data tell you? So I suppose that part I will own to, but not understanding and quite honestly, some of the machine learning algorithms that we're using today did not come out of academia, right? They came out of our students that went to industry, but they came out of industry, most of them. So it's this combination of things that allows us to do things today that it's hard to predict. Yeah.
Just a few thoughts. I don't know what's are we on the current is fourth?
Well,
That's what you're.
We would like to be on fourth, but I would argue in many cases we're not there yet because we don't have enough data.
And so one point that I wanted to make, maybe mostly for the students, I think everyone understands this, but data-driven science has always been data-driven. That's the only thing we have, right? The physical sciences, right? The Schrödinger equation, the Maxwell equations that you had, F equals ma, they all come from data. And then we had very smart people that came up with a way with a few data points to come up with these generalizations and these mathematical ways of describing that. But nothing out of whatever we teach you comes from any other place than data from the very beginning. Now, the tools that we use are a little different, and then data maybe is more prominent, and that's why people use data-driven. But all of those paradigms were data-driven. In terms of what comes next, I have no idea, and every time I try to think about what's coming, I get it completely wrong. So with that caveat, I think there's a lot of interest in, well, there's a very interesting paper that I encourage students to read. It's the Turing Nobel Challenge. And it's written by a biochemist. And the idea is, can you design a system that can, just like the Turing test, can design and execute Nobel quality research in a way that's indistinguishable from a human researcher. And it's an interesting read. And that goes to what Kristin was saying. The other interesting trend is how do you derive knowledge from the data? So we have the data. Can you then abstract that into knowledge? Okay, how is data related? What can you infer from X, Y, and Z? And that, I think, we're just scratching the surface of doing that, right? And this is what I think, when we're going back to the first question about education, hypothesis testing. Of course, there's ways of using ML to create hypotheses, but that's what type of questions you ask. How do you relate A and B? That's, I think, where there's more work to do to bring AI into science and engineering.
Yeah, great points raised there. If I can build on what Ali was saying, this is an interesting question, but it's for example, yes, science was always data-driven, right? Like some common examples that people use are Hall-Petch equation, Hume-Rothery, miscibility, like rules and stuff. All of that came from data, right? And that was like 50s, maybe even earlier that it started. In terms of the fifth paradigm, if we are to assume that, okay, we are in the fourth paradigm, then maybe a couple of things I can think of is one, like the Turing challenge, maybe the fifth paradigm is like truly completely autonomous science, which is that you tell the computer, you tell Jarvis, here is my problem. Can you solve it for me? And it does everything from step 0 to like step n, whatever, right? It completely figures out what has been done before. Okay, here is a possible way to do it. Here are the experiments we need. Here are the simulations we need. Here are the models we need. Blah blah blah. It builds on what has come before and then completely figures it out. I mean, then is there any need for the scientist there, for the person in the lab? I'm not sure. And you can argue that this is part of the fourth paradigm in itself, but obviously so I do think some kind of an autonomous, completely autonomous research, autonomous synthesis, characterization, like which efficiently works and you can trust it, right? That might be it. The other answer I have is that maybe something catastrophic happens to the world and there's an apocalypse. We go back to the first paradigm, and then we have to start doing simple experiments again, and then let's discover everything again from scratch. But this time faster, because those who survived probably remember things, right? So
On that positive note.
Sorry, I watched too many movies.
Thanks, Dave. Yes, so barring an apocalypse, thinking about the data that the materials scientists could benefit from most, what is missing for you on the metrology and the characterization of materials to devices, to systems using those materials? And what are the steps to get there?
Question, I think.
So I've advocated to foundations in places because I don't think this is something that the NSF or DOE will fund. Is this more establishment of more gold standard data sets from experiments, because we need them to benchmark against. And I think we've sort of there aren't a lot of incentives for collecting that kind of data today in experiments, which ties back to automation and robotics. Instead of sending an army of poor graduate students out there, and you're all individuals, which means you're going to all get slightly different data as well, but a robotic setup will make the same systematic errors or better things. So I would argue for more automated robotic setups of obtaining gold standard data sets would be extremely useful. Also for anchoring all of those machine learning things. I mean, I'm a little bit worried sometimes that all I do is trust DFT, because once I've checked those 200 data points, that's it. I can't do anything more. And then I sent people into the lab to make a material, and we found out that pseudopotential with terbium was bad. That has happened. And you couldn't make that compound because we literally used a bad DFT pseudopotential. So, okay, that's one thing I would ask for. I would also ask for better, and this goes back to what Ale and we were saying, that we need to treat our data better. There is actually a lot of data being produced in our academic world, and most of it goes into papers, and they sort of disappear, and it's very hard to extract back in the provenance that they were created. So instead of the gold standard being publish a paper in Nature, maybe the gold standard should be just put your data with provenance somewhere. Do that first, and then go for the Nature science. That's what this is what we, as a community today, reward, Nature and Science papers. Maybe we should change that a little bit, because that will change how much we accelerate going forward. So yeah, automation, data sets, changing the reward system.
And data sets on failed experiments.
Yes, yes, that too. And that goes with the robotics too, because I have not had success of telling experimental students to put their failed experiments into a notebook, but in computations, we log everything, including the failed computations, right? And we learn from that. But now with the beginning of robotics, so A-Lab, my experimental partner, and the baby of Herbrand Sader at Lawrence Berkeley and UC Berkeley, they log all their failures too. The only way you can do it, in my opinion. Yeah.
And it's not failure in the sense that the experiment is wrong. It's a
Experience.
negative result, right? It's something that things were done correctly, and then you get a result that maybe you didn't like. And that is a big challenge, because the literature does not contain negative results, and that biases the models that we create. I think the workflows. Okay, I think we need, I 100% agree. We all say the same thing. Of course, we all like to publish in high impact journals at the same time. But I think the analogy I like to make is with publishing music. I think how we share the outcome of our research is completely backwards. And so we more or less publish 5 million papers per year globally. And that's the same number of songs that are published every year. You can ask every middle schooler in the country to find the song, and in 2 seconds, they will be able to not just find the song, but play it for you, okay? Now, ask a PhD student that has been trained for years to find data and use it, and it takes us 6 months, okay? And if you look at how we share scientific knowledge, the first paper was published, it's acknowledged that the first paper was published in 1666 in the UK. And you can go find the PDF of the paper, and you can look at scientific papers a century later, 2 centuries later, and today, and they look exactly the same. Okay, so from 1666, the papers have not evolved one bit. And think about music, right? In those days, you have to go to the royal palace to listen to music and be invited, and now we stream it. So we need to rethink how we share the outcome of our work.
Yeah, not too much to add to these points, but it's a question that I really like, which is, I'm a computational scientist as well. So what do we want from experimentalists, et cetera, right? So just building on what these guys said is that, of course, all the data to be there, right? Like, just more of a push to digitize your data, to log your data, to have it there in a machine readable format if possible, but like just in a format that can be utilized, that can be readily, read by a machine and then used for comparisons with other work, etc. One of the things I quickly wanted to mention was that I've talked about this with my collaborators, which is that to benchmark our computations, it would be great to get like a very, very specific experiment, right? And oftentimes there is not that much of an incentive to do it. Like, for example, I study defects in a solid state material. So I create a model, I put a defect in it, I calculate a property, and then I try to compare it with the experiments. It doesn't often work because no matter how the experiment was done, there was some impurity or there was some other factor at play, or like, there was, no, you didn't take this phase into account, or, you didn't take that into account. So like somebody, like, my collaborator was telling me, like, I kind of what I want to do is pick like a class of semiconductors and create like a highly pure, 99.9% pure like sample of it, and then so that I have atomic scale precision, and then I can induce exactly the dopant I want and see what happens, right? And then that can be matched with my DFT maybe, right? But are funding agencies necessarily gonna help us do that? Is that going to lead to a Nature paper? Because this might not give us anything in the end, right? It may not work, right? So yeah, so it's an open question, I would say, like, if we can use experimental data more effectively to improve the computations, and of course, if we can make sure all the experimental data is out there and the experimentalists also understand how the computations are being done, so that there's less of a barrier between that, right? So those are just some points that I wanted to add there.
Any other questions from the audience?
Thank you. So throughout all of these talks, we've kind of been talking a lot about DFT and models that are trained on DFT at a lower fidelity but higher efficiency. And I'm curious about if you see a kind of loss of information from not using higher order models that might use electron phonon physics or other interactions that DFT doesn't consider.
So yes, DFT is certainly the workhorse, but at least in the materials project, and I'm sure other people do that too, we use higher order methods as well as experiments to anchor some of the deficiencies of DFT. So for example, the O2 molecule doesn't have the energy that the O2 molecule gets out of ASP. We correct it. We correct N2, we correct S8, we correct peroxides, superoxides, because they're also tremendously bad out of DFT. And typically that comes out of either those higher fidelity methods or experiments. So that's also where sort of, again, these other data sets that are better in certain ways should be combined. That is, in what I would say, a challenge for the community too. We tend not to always talk to each other as much as we should, but if these data sets, we keep coming back to data sets, get shared more, we can integrate them. So if people working on quantum Monte Carlo or, very vibrational methods, they were to share their data sets more, systematically, we can incorporate those and we can sort of figure out where are the little inefficiencies, and maybe if they can't calculate as many compounds as we can, but we can incorporate that learning into the DFT, and because DFT is systematically wrong, it tends to do rather well. So we do already to some degree do that, but we can certainly do better.
Well, and I think it has to, so Kristin is a magician at making DFT do things that are very hard. And you would
Doesn't
think,
really want to do.
yeah, it shouldn't be doing this, and she gets to work, and that I appreciate that. But obviously, there's lots of properties that depend on microstructure, that depend on characteristic scales that are way beyond what DFT and maybe even molecular dynamics with intraatomic potentials can do directly. So this old paradigm and old idea of multi-scale modeling is still very valid. And I think we need to think, DFT has a lot of advantages for a bunch of reasons that we can discuss. It's very systematically wrong, not too wrong, but systematically, so you can make a lot of decisions based on DFT. That's not the case necessarily in using some other methods. But it is important to bring up those methods up to the level where we can actually use them for decision making. And of course, CalFAD is used all the time in materials design and alloy design and whatnot. So I think our toolbox has to be every tool under the sun that captures the physics and can be validated and is validated. That's the importance of data. And then you can use to extrapolate and to explore.
Yeah, just to quickly make a point related to that, since the question is about DFT, if I understood correctly, density functional theory, not everybody here might know what DFT is, by the way. So that's, it's a quantum mechanics-based, method to study the structure and properties of materials, right? So you're solving the Schrodinger equation using a bunch of approximations. So there are inherently approximations, and there are many levels of theory that you're using in DFT. The lowest one will help you do it very quickly, but it's not going to be accurate. As you go up the ladder, it's going to get more accurate, but it's more expensive. And then if you're doing it for 10 atoms versus 100 atoms versus 1,000 atoms, there's a big difference, right, in the expense there. So, I think the important thing to keep in mind here would be to be aware of the inherent limitations of DFT, right? What you need to ensure is that you're getting numerical accuracy, right? Which means that whatever level of theory you're using, the result you're getting is correct, right? Is mathematically correct. Whether it's going to match with experiments, I mean, it's probably not. Let's be honest, right? But but that doesn't mean it's not useful, right? So there is a logic to using it in a qualitative sense, right? Or you can apply like an error bar. You can say that on average, I know that this is 80% accurate, so then that helps you extend it, right, to get that accuracy, right? But I would say in terms of DFT itself, if more people are aware of, here is what DFT can do, here is what it cannot do, and in many cases it can help you, but it cannot exactly show you the result, right? This is what it is, right? So if more people understand that, then I think it will be more effective to kind of, use DFT as a tool itself, right? Not to get into the specifics of electron phonons and temperature, dependent properties and things like that, but just understanding, the strengths and weaknesses of it as we currently have it, right?
Go ahead.
So kind of building on this a little bit. So when I was a grad student, which probably was a little bit earlier than you guys, but not too much earlier, Mike Baskus told me, I was talking about computational stuff because he was my boss's boss at Sandia. And I asked something about, well, how many atoms could you simulate in that, fancy embedded atom model that they did? And he said, even if I could do more, it wouldn't necessarily help me build a better bridge tomorrow. And it was really interesting, there are places where using the right tool for the job, this wasn't it, and he didn't see any point where it would ever be it. And there were probably better ways to build a bridge than knowing where every atom in the bridge was. So how do you use platforms that share materials data to say, this is good for this range? How do you put a boundary so that people, or should you put a boundary and say, this is good for this, we recognize beyond this, they're like dragons and maybe you shouldn't go there? Or do you say light it up, see if you can do something with it?
depends on the property. So in terms of defects, right, it all depends on whether those defects are far in between. Then you can use a small box. If there's these, then defects tend to talk to other defects, which could be long-range clusters of defects. You might be very wrong if you only consider a point defect with nothing else. Diffusion properties tend to go with the bottleneck of the diffusion. If you manage to locate the diffusion bottleneck, you can do a very small supercell. But if you're getting it wrong, then it is irrelevant. Anything that's mechanical properties, we talked about, microstructure. You right away, in where dragons are, but you can very often, going back to the point about, is it useless if it's not exact? You can very often make an estimate, like some sort of this is where it's not going to be higher than this, it's not going to be lower than this, it's going to be somewhere in this range, depending on X, Y, and Z. So making educated choices and having an error bar and thinking about that, I think maybe that's where Mike was going. Or maybe not. Maybe he was just tired of answering that question. Because we get that question a lot. Like, how many atoms can you do? 200.
Oh, he was up like 1,000 then.
Well, he was probably also some internal politicking about large-scale MD versus what he was doing. But I think that's going back to the first question and work education, right? That's where the domain expertise, this is what this community needs to reserve to ourselves. We know what we're doing. The fact that the tools are more widely available, just like with GPT, okay? The fact that you can ask a question, you get an answer, or press a button on NanoHub and run a simulation, or download a lot of data from the materials project, you're not delegating the decision-making authority to the system that you're using, right? You are the user, you are the student, you're the researcher, you're making the call as to whether that answer that you have is something that you're going to go to the bank with, right? That you will never be able to tell your boss, well, GPT told me, right? That's not going to be an excuse. Or the materials project told me, I downloaded data and that's what they said. Well, no, you are supposed to, that's your domain expertise, and that should not be delegated, right? So we're all, again, lowering the barriers is great, and I'm a huge proponent of that, and that's what we've been doing with NanoHub, but that doesn't allow you to run DFT simulations without knowing the Schrödinger equation, without knowing the Kohn-Sham equations and the pseudopotentials, right? You were talking about you had to create your own pseudopotentials. But 20, 30 years ago, you had to know because you couldn't do it otherwise, right?
And we still use bad ones. We still use bad ones, right? I mean, everything that VASP puts out there isn't all perfect. It's their best educated guess. That's something that might work, but you have to use it with that domain knowledge and discretion in place. Don't use it as a black box. I know we say that a lot, but use your knowledge.
So when we talk about automated or even autonomous systems, you have to think, what do I delegate to the system? What authority do I delegate, and what authority I'm keeping to myself? And when we provide tools, I think when we try to lower the barriers, we're not taking that responsibility from the user.
Yep. Excellent points raised there. Going back to the point I made earlier is like, if you want to use DFT, you probably want to be aware of what it does, what it doesn't do, right? And you certainly need to know. Yeah, not probably. And also, you should not be using it as a black box necessarily, right? Where somebody asks you to calculate an elastic tensor and you use DFT to do it, it may give you a value, but you can't trust it blindly, right? This is it. This is the answer, right? So again, it goes back to what I was saying earlier, which is that if you're aware of, how that theory works, right, then you will know, whether this is going to be reliable or not, or to what extent. And DFT necessarily isn't going to predict, what you want it to, but it might help you explain things, right? oh, like, this bond is weaker than the other bond, or like, there's what's going on with the electrons and stuff like that, right? So specifically, that's what I would say to build on what, what Dr. Perrson and Dr. Strachan are saying here is to, domain expertise is important, understanding the theory is important, but if somebody wants to build a better bridge, maybe maybe DFT is not where you start, depending on your problem, right? If you want it to come in 6 months, then maybe DFT is not where you start, right? But if you have like a big chemical space, you're interested in chemistries, right? I just want to know whether this material will be stable or not. DFT might be pretty good for that, right? Because that's where you can kind of, at least you can predict it's somewhat like it's, thermodynamic stability as a starting point. That doesn't build a bridge for you. There's so much more to come after that, right? So, yeah.
Other questions? So touching on that, starting from that, you discussed some challenges such as the data quality. So I was wondering if you can elaborate on that, and also maybe ethical concerns that you already started discussing.
Yeah. That is a great question. So we were talking about, please everybody make your data available, but I guess there is a risk involved in that as well, right? Because who is going to like gatekeep like the quality of the data, right? Because if you are an expert in a certain type of experiment and somebody else did that, you may or may not be happy with that, right? Like if you are an expert, right? That's why we are all experts in different areas, right? You may look at it and say, no, like the NMR, example, right? You may look at it and say, oh no, like this is completely wrong, like what you've done, or this is not the way that I would do it. Somebody with a 20-year experience in it. So the data quality question is actually very important, right? So like I have done some work where I use computational data and then include experimental data and then put labels for it, right? This data is from experiment, this data from computation, and you can kind of do like multitask learning, multi-fidelity learning. But then if you start including labels for, I trust this data 90%, whereas this data is 40%, that's going to complicate your machine learning model completely, right? Like, the best thing to do would be if you don't trust a data point, you just remove it, right? Then you have a data scarcity problem, right? If you can't validate, how good a data point would be. So I think the community as in general should probably have more discussions about this. I mean, there are, funding agencies are interested in this, like, in terms of open science and stuff, the quality of the data is important, right? That's why all the data has to be fair. It has to be reproducible, right? So somebody reproduces it and it's correct. So then there is a confidence that, okay, this was done correctly. I reproduce some of the data, it looks good, like, that kind of thing has to be done, right? That there has to be a mark to every data set, right? This is quality, this is not tested yet, or whatever, right? Ethical concerns, like, that is a more interesting question. I mean, I'm not sure in terms of what, like, if like people are faking data or like people are stealing data, like, even like the large language models, as everybody would be aware, like ChatGPT is kind of trained on billions or trillions of text, that it got from somewhere, right? So in terms of, is it ethical to train your models on people's papers, for example, publications, like, there are permission issues there, etc. Of course, there are papers that are retracted because their experiments are not reproducible. Making data fair will solve these problems, right? That having that reliability in that data would solve that. So, I mean, I'll let, the others kind of chip in about the ethics part of it more, I guess.
Just two things. One is, data quality, I think is one of the, and concerns about data quality and being judged by your peers is one of the main limiting factors why people don't share their data. And my concern with that is you still publish the paper with a few selected results and you hide the data set that leads to that. That needs to go away, right? So I think if we're honest, if we're doing research and we're going to write a paper, we share the data. And then if the data, someone shows later on that the data had issues, then of course you can retract it, you can correct it, and it's an honest mistake. This is way better a method to make progress than being cagey with the data, publishing a few data points in a way that no one really understands how the data was generated, and then those errors get propagated forever. In terms of ethics, there's lots of issues to think about. One of them is delegation of authority, and that's something that I think we need to discuss. The other thing is because we need data, it's what people tend to call consensus science. Okay, that there's as a community we tend to agree on certain things and move in certain directions, and if the field moves in a direction where you need lots of science, it's going to be potentially harder for new ideas and new fields, or somewhat that comes with a completely radical new idea, or an area that maybe it's underlooked. If you think about disease and what type of populations are represented in the data that we utilize, or the type of engineering problems that we solve based on the data that gets generated, that might lead to, there might be ethical considerations underlying those decisions.
Yeah, I am a fairly cynical person, so I believe that whatever tools we end up developing are going to be used both for good and for bad. That's humanity. The only thing we can do, in my opinion, is try to stay 2 steps ahead of the bad guys, or at least try to mitigate it as much as possible. So, of course, making data available is going to be, in some cases, misused. Right. But by and large, I think it's a good idea, because we will be able to catch people who are hiding their data, people who are maybe overinterpreting some trends when they shouldn't be, people making up data. It's much easier to catch if they submit their data set with the paper in an easily analyzable form. So I suppose I am a big proponent also of, like, let's just make it open, and I'm going to rely on all the people out there to make this a better world.
I'll just quickly add to that what Ale was saying, that people are a bit scared sometimes to share the data, because they're like, what if somebody comes and tells me? Yeah, what if I made a mistake? I have to be honest, I thought that too. When I was a PhD student, and I was like, I should put it out there. But what if somebody emails me tomorrow saying, you did this wrong, or whatever, right? You have to be prepared for that, basically, right? You have to accept that. I mean, that's actually a good thing. If somebody reaches out to you and say, I think you may have made a mistake.
It's great. Do you know how many mistakes there are on the materials project? We try very hard to remove them. Every time somebody tells us, we fix them, we do better. But it's amazing to have lots of people eyes on that data set and working together to make it a better one. So at some point, we should just embrace it. Science is 1 step forward and 2 steps backward sometimes. And if we work together, we'll do it better.
All right, just one more.
Hello. Okay, so I'm thinking about the importance of, like, having this domain expertise and then having completely fair data, and then seemingly these autonomous labs being the best way to ensure that we get all these positive and negative results in, like, a very systematic way. So with this said, like, do you see the field as more likely to grow? Like, I think it has recently, with more and more material classes popping up with sort of different localized interest groups, or becoming a bit more concentrated around these autonomous workflows where they might much more easily branch out to similar material classes.
Yeah, I'll very briefly start, but so I think there's always going to be a sort of a role for scientists that are very sort of focused on a particular problem or a theory development and are not doing automation at all, as well as the people doing automation and scale up and working with industry. So the whole spectrum is needed. I don't do improvements of density functional theory, but I am so grateful to the people who do it, because without those people, I wouldn't be able to improve what I'm doing, by and large. So I think that they're all needed. Yes, I think there is a excitement about automation and what it will do for our field because we didn't have it that much before. And we have now recognized that the fourth paradigm is happening, and it's happened mostly because of computations. We need to bring that into experiments too. So automation is going to be needed for that. So I think it's more about that. We've seen a need and a gap, and we're trying to fix it. So that might be more of that. And I personally, I've seen the students work on automated workflows for computations, automated workflows for experiments. And there's something exciting about being a pioneer, like doing something that nobody's ever done before and figuring things out that hasn't been solved. And sort of, I think that's maybe a bit of what you're seeing. Doesn't mean that the other things should go away. We kind of work together.
Yeah, I suspect. So certain workflows are easier to automate than others. I think there's always going to be a need, at least for the foreseeable future, of students, researchers working there and connecting hoses and fixing things and pushing things around. And now, once you've figured out that workflow, if it's at all possible, automating is the way of generating consistent data, doing work that's repetitive, that's not the best use of a PhD quality student doing the same experiment over and over and over, right, or running the same simulation by hand a gazillion times. And so I think that's, this is what we need to think about. What skills do we need to retain and what skills do we delegate to automation, right? And what are the students going to do? How many workers are we going to replace with automation and with AI, even at the PhD level? Okay, this is something that has not happened in the past.
Well,
this is probably
happened in industry. I mean, we don't build our own cars anymore.
Well, but
Thankfully.
not PhD level. I agree with you. Of course,
So,
at other levels, this has happened. And I think for the first time, this might happen at the PhD level. Okay. And so the question is how, as a community, we readjust ourselves.
Yeah, I don't have anything to add.
I'd like to thank the panel and thank you everyone for being here. Thank you, Dr. Perrson. I appreciate it.